In this video, we're looking at the derivative of a vector. It's our first lesson in the vector calculus unit, which is looking at derivatives and integration of vectors. Okay, so we'll look at the definition of the derivative of a vector, and it is pretty straightforward. If we have a vector function r with parameter t, which is in component form x with respect to t in the I direction and y with respect to t in the j direction, the derivative of this vector will be denoted by r dot, and we'll be looking at the derivative of x with respect to t in the I direction and the derivative of y with respect to t in the j direction. So that simplifies down to the derivative of the function, the vector function r being the derivative of x in the I direction and the derivative of the y component in the j direction. Okay, so that's pretty straightforward. This is a derivative of the individual components with respect to t. Okay. When we look at the double or the second derivative, which will be very important, we're going to denote that by the two dots on top, the derivative of the vector function. It will be the double derivative of x with respect to t in the I direction and the double derivative of y with respect to t in the j direction. So that means we end up with the double derivative being the double derivative of x function in the I direction and the double derivative of the y function in the j direction. So again, it is just the double derivative of the individual components with respect to t. The definition of the derivative of the vector is quite straightforward. So we'll look at a couple of examples so you can see how this works. Okay, so in this first example, it's pretty straightforward. For the vector function, r is equal to 20t in the I direction and 15t take 5t squared in the j direction, find the single and double derivatives. So for the single derivative, we're looking at the derivative of 20t in the I direction, so derivative of 20t is 20. And the derivative of 15t take 5t squared in the j direction, so the derivative of 15t is 15. And the derivative of negative 5t squared is negative 10t. So the derivative is 20 in the I direction and 15 take 10t in the j direction. When we look at the second derivative, we'll continue on from the first derivative. So the derivative of 20 is 0, so 0 in the I direction. And the derivative in the j direction, derivative of 15 is 0, and derivative of negative 10t is negative 10. So we're left with negative 10j. So that means our second derivative is simply negative 10j. And it's as simple as that. There's our first and second derivatives. Okay, so in this second example, it's asking us to find the derivative of the vector function in 3 dimensions. So the first derivative of cos, is going to be negative sine t. The derivative of negative sine t will be negative cos t. And the derivative of 5k is 0. So now we're left with that first derivative of negative sine t I subtract cos t j. Now when we look at the second derivative, the derivative of negative sine is negative cos, and the derivative of negative cos will be positive sine. So there's our first derivative and our second derivative. Nice and simple. Okay, so again in the next example, we're trying to find the first and second derivative. The only difference is the function is a little bit more complex. So we're looking at exponentials. So when we look at the first derivative, the derivative of e to the power of t is simply e to the power of t, so that one's nice and easy. When we look at the derivative of the next function, we have to look at them one at a time. So this first one that I'm about to highlight is going to be a chain rule, because we have a function within a function. We've got e to the power of t take 1 raised to the power of 3. So that means we're going to have 3 multiplied by e to the power of t take 1 to the power of 2. So it's a polynomial on the outside, and we need to multiply by the derivative of the inside, which is e to the power of t. Now the derivative of 1 is going to be 0, so we can drop that off, and we end up with, simplified, the derivative function being e to the t I, and 3e to the power of t, e to the power of t take 1 squared in the j direction. Now the second derivative is going to be a little bit more complex. So in the I direction, again, it's nice and simple. The derivative of e to the power of t is e to the power of t. The problem is with the j function, we're looking at a product rule where u is equal to 3e to the power of t and v is equal to e to the power of t take 1 all squared. Derivative of u is going to be 3e to the power of t, and derivative of v is going to be a chain rule in itself, so it's going to be 2e to the power of t take 1 and multiplied by the derivative of the bracket, which is e to the power of t. So we end up with 2e to the power of t multiplied by e to the power of t take 1. So it's a product rule where we're looking at the derivative being vu dash plus v dash u. We end up with this pair. So 3e to the power of t, e to the power of t take 1 squared. And this pair, which is 6e to the power of 2t, e to the power of t take 1. Okay, so in the j, it was a lot more difficult. And we end up with 3e to the power of t, e to the power of t take 1 all squared, and 6e to the power of 2t, e to the power of t take 1. And we can simplify that slightly because there's a common factor. So we can take the 3e to the power of t and the common bracket of e to the power of t take 1 out. And what we're left with is e to the power of t take 1 and 2 lots of e to the power of t in the j direction. So we'll finish off that line. And finally it simplifies down to 3e to the power of t, e to the power of t take 1, and 3e to the power of t take 1 in the j direction. Filter that one out a little bit so it's not getting in the way. Okay, and that's it. A nice challenging derivative. Okay, in this last example, we're looking at the curve described by the vector equation or vector function r is equal to 2 cos t in the I direction, 3 sin t in the j direction. For part A, it's very straightforward. We want to find the first and second derivative. So the first derivative of cos is negative sine, so we've got negative 2 sine ti. And derivative of sine is cos, so we get 3 cos t in the j direction. Nice and easy. The second derivative is going to be the derivative of the first derivative. So derivative of sine is cos, and derivative of cos is negative sine. So it means we end up with negative 2 cos ti subtract 3 sine tj. Now, if we're going to find the gradient when x is equal to cos t and y is equal to 3 sine t, essentially what we're looking at is we're trying to find dy dx, but because we've got everything with respect to t, we'll have to use a process called related rates. Now, if we split this, we have dy and dx, but we need a common value in between that relates them both. So in this case, it's going to be dt. So see, it's still technically dy dx, and the dt's would cancel out, but we're going to use their individual component values. Now, it should be noted that this dt dx is actually just 1 on dx dt. Okay. Now we have dy dt and we have dx dt, so let's set this up. Now, from above, we can say that dy dt is going to be equal to 3 cos t, and dx dt, so this is dy dt, and this is dx dt, so dy dt dx dt, dx dt will be equal to negative 2 sine t. So that means when we're trying to find dy dx, then we can say it's 3 cos t multiplied by 1 on negative 2 sine t. So that leaves us with negative 3 on 2 cos t on sine t. Now cos on sine is cot, so negative 3 on 2 cos t. Okay, that'll be our derivative, or our gradient, when x is equal to 2 cos t and y is equal to 3 sine t. Okay, that concludes our lesson on the derivative of vectors.